All right, this is Unit 2, Lesson 4, Complex Numbers and Operations. So our lesson essential question is, how can you represent and operate on numbers that are not on the real number line? At the end of this lesson, you can solve problems with complex numbers. So example number 1. All right, example 1, solve a quadratic equation using square roots. So how can you use square roots to solve the equation x squared equals 16? Well, if I take the square root of x squared and the square root of 16, we know that 4 times 4 gives me 16. And then I should have plus or minus square root of 16 or plus or minus 4, because negative 4 times negative 4 also can be 16. So the solution of the equation x squared equals 16 are 4 and negative 4. So how can we use square roots to solve the equation x squared equals negative 9? There are no real numbers that you can square that result in negative 9. However, you can simplify the expression by extending the properties of radicals. X squared equals negative 9, so x equals plus or minus the square root of negative 9. I can then break negative 9 down into 9 times negative 1. The square root of negative 9 is 3, and the square root of negative 1. The solution of this equation x squared equals negative 9 are not real numbers, but are part of a number system called the complex numbers. A number, the square root of negative 1, is called the imaginary unit I. Replacing the square root of negative 1 with I allows you to write the solutions to the equations x squared equals negative 9 as 3i and negative 3i. So let's try it out. Use square roots to solve each equation, right? Your solution using the imaginary unit I. So I'm going to take x squared equals negative 5. So I'm going to take the square root of x squared equals the square root of negative 5. Well, negative 5 I can write as negative 1 times 5. 5 isn't a perfect square, so if I were to take the square root of it, I would actually get a non-repeating decimal. So x equals, we do know that negative 1 equals I squared. So that means x equals plus or minus I square root of 5. I then have x squared equals negative 72. So 72, I can actually break down into negative 1 times 72, which also breaks down into negative 1 times 36 times 2. 36 is a perfect square, so I can actually when I square root this, I can actually take the 36 out as well. So x equals plus or minus 6i, because the negative 1 and the 36. So the square root of negative 1 is I, and the square root of 36 is 6. And of course, I still have the 2 left underneath this, under the square root. All right, the concept. Complex numbers. The imaginary unit I is the principal square root of negative 1. Then I squared equals negative 1. An imaginary number is any number b times I, where b is a non-zero real number and I is the square root of negative 1. Complex numbers are numbers that can be written in the form a plus bi, where a and b are real numbers and I is the square root of negative 1. They include all real and imaginary numbers, as well as the sum of real and imaginary numbers. For example, negative 6 plus 4i. A equals negative 6 and b equals 4. 7 minus I square root 2. A equals 7 and b equals negative the square root of 2. 0.5i. A equals 0 and b equals 0.5. All right, example 2, add and subtract complex numbers. So just like you did back in Algebra 1, where you were adding and subtracting integers, you're going to do the exact same thing where you're adding and subtracting complex numbers. What is the sum of the quantity 4 minus 7i and the quantity negative 11 plus 9i? And adding or subtracting two numbers in the form a plus bi, combine the real parts and then combine the imaginary parts. The sum or difference may include both a real and imaginary part and can be written in the form a plus bi. So if I look at it, 4 minus 7i plus negative 11 plus 9i. The 4 are my real parts. So I'm going to add those together, 4 plus negative 11. Then I have 7i, negative 7i plus 9i. I can add them together. They're my imaginary parts. You can almost think of I as a variable. So negative 7 plus 2i is my final answer. 4 plus negative 11 gives me negative 7, and negative 7 plus 9 gives me a positive 2. How can you add and subtract complex numbers? What is the difference of 6 plus 8i and 2 minus 5i? So if I'm going to subtract, I need to distribute this negative sign to the second portion of my expression. So 6 plus 8i stays the same, plus negative 2 plus 5i. So I distributed this negative sign to the 2 and the negative sign to the 5i. Remember, it's like multiplying by negative 1 to everything on the inside of your second equation or second expression. So then I can add together my a values or my real numbers. 6 plus negative 2 gives me positive 4. And then 8i plus 5i gives me 13i. All right, so let's try it out. Find the sum or difference. So the first thing I'm going to do is I'm going to put my real numbers together. Negative 4 plus negative 2. That gives me negative 6. And then I'm going to add my imaginary units together. 6 plus negative 9i equals negative 3i. So then I have negative 6 minus 3i. Negative, or 3 minus 2i minus negative 4 plus I. So I'm going to rewrite this expression, distributing the negative sign, which would give me negative, negative makes a positive, negative, positive makes a negative. Okay, then I'm going to go ahead and add my real numbers together. 3 plus 4 is 7, and negative 2i plus negative I equals negative 3i. So I have 7 minus 3i. All right, example number 3, when I'm multiplying complex numbers. So how can you write each product in the form a plus bi? So I have negative 2.5i times 8 minus 9i. Now all you're going to do here is take what's on the outside of the parentheses and multiply and distribute on the inside. So negative 2.5i times 8 minus negative 2.5i times negative 9i. Negative 2.5i times 8 is negative 20i, and then negative 2.5i times negative 9i is positive 22.5i squared. Remember, treat the I as though it were a variable. Okay? I squared we know is negative 1, so I substitute negative 1 in for I squared, which gives me a negative 22.5. So then when I rewrite this in the form a plus bi, I have negative 22.5 minus 20i. How can you write each product in the form a plus bi? Now I have 3 minus 2i times 3 plus 2i. So I'm going to FOIL this out. 3 times 3 plus 2i minus 2i times 3 plus 2i. So I get 9 plus 6i minus 6i minus 4i squared. I squared again is negative 1, so I substitute that in. So I get 9 plus 6i minus 6i. This is going to multiply to be positive 4. 9 plus the 4 gives me 13. And then 6i minus 6i cancels each other out. So the product is just 13. All right, so let's go ahead and try it. Write each product in the form a plus bi. I'm going to take 2/5 I times 10 minus 5/2 I. So when I multiply through, 2/5 I times 10 equals 4i. And then 2/5 2/5 I times negative 5/2 I equals negative 1 I squared. We know that I squared equals negative 1, so we substitute that in. Negative 1 times negative 1 equals positive 1. So when I write this, I have 1 plus 4i. The next one I have is 1/2 plus 2i times 1/2 minus 2i. So I'm going to FOIL. So I have 1/2 times 1/2 equals 1/4. Then I do 1/2 times negative 2i, which equals negative I. Then I have 2i times 1/2 equals positive I. And then I have 2i times negative 2i, which equals negative 4i squared. We know that I squared equals negative 1. So that means negative 4 times negative 1 equals positive 4. Now I have 4 plus 1/4 minus I plus I. So I get 4 and 1/4 as my answer, which is also 17/4, which is also 4.25. So complex conjugates. So complex conjugates are complex numbers with equivalent real parts and opposite imaginary parts. So their product is a real number. So this is actually really helpful when we're going to be dividing by complex numbers. You can actually take that complex conjugate and multiply it by the numerator and the denominator, and you get a real number in the bottom. So for example, 7 minus 8i, its complex conjugate is 7 plus 8i. Negative 2 plus I, complex conjugate is negative 2 minus I. So the real part stays the same and the imaginary part flips signs. All right, example number 4, simplify a quotient with complex numbers. So how can you write this quotient 10 over 2 minus I in the form a plus bi? So when the denominator has an imaginary component, you can create an equivalent fraction with a real denominator by multiplying by its complex conjugate. So 10 over 2 minus I equals 10 over 2 minus I times 2 plus I over 2 plus I. So I use the complex conjugate of the denominator to multiply by 1. So I'm really not changing the value of it. I'm just allowing myself to have easier access to a denominator. So I multiply 10 times 2 plus I and 2 minus I times 2 plus I. Well, when that simplifies, I get 4 plus 2i minus 2i minus I squared. When I multiply that through, I squared, of course, is negative 1. When I simplify, I get over 5. I can divide 10 and 5. They simplify from each other. 10 divided by 5 is 2. So I get 2 times 2 plus I, which I can then multiply through. 2 times 2 is 4, and then 2 times I is 2i. All right, so let's go ahead and try it. Write each quotient in the form a plus bi. So I have 80 over 2 minus 6i. So 2 minus 6i, and the complex conjugate for this is 2 plus 6i. So I need to multiply 80 times 80 over understand why it does that. 80 over 2 minus 6i, and I'm going to multiply that by 2 plus 6i over 2 plus 6i. So when I do that, I get 80 times 2 plus 6i over 2 times 2 is 4. 2 times 6i is 12i. Negative 6i times 2 is negative 12i. And then negative 6i times 6i is a negative 36i squared, which simplifies. So now I have 80 over 2 plus 6i. Simplifies, so then I have 4. The 12i minus 12i, they cancel each other out, and I get positive 36. This equals 80 36 plus 4 is 40. So 80 over 40 simplifies to so 80 divided by 40 is 2. So I get 2 times 2 plus 6i. This equals 4 plus 12i. For B, 4 minus 3i time or over negative 1 plus 2i. So negative 1 plus 2i, its complex conjugate is negative 1 minus 2i. So I need to multiply through 4 minus 3i over negative 1 plus 2i. And I'm going to multiply it by its complex conjugate. That's going to equal 4 minus 3i times negative 1 minus 2i. Actually, I'm going to go ahead and just simplify as I go. So this gives me 4 times negative 1 is negative 4. 4 times negative 2i is negative 8i. Negative 3i times negative 1 is positive 3i. Negative 3i times negative 2i is positive 6i squared. Okay, negative 1 times negative 1 is 1. Negative 1 times negative 2i is positive 2i. Positive 2i times negative 1 is negative 2i. 2i times negative 2, positive 2i times negative 2i is negative 4i squared. Okay. Then, of course, I squared equals 1, so I have negative 4 minus 8i plus 3i is negative 5i. And I squared is negative 1, so that gives me 6. Okay, then I have 1, 2i minus 2i cancels, 4i squared becomes positive 4. This equals negative 4 minus 6 gives me negative 10 minus 5i over 5, which equals negative 10 divided by 5 is negative 2. And negative 5i divided by 5 is negative I. All right, example number 5, conceptual understanding factorize sum of squares. So how can you use complex numbers to factor the sum of two squares? How can you factor the expression x squared plus y squared? Well, I know that x squared and y squared, I can just multiply x times x to get me x squared and y times y to get me y squared. I can rewrite x squared plus y squared as the difference of two squares, x squared minus a negative y squared. And then how can negative y squared be a perfect square? You can think of negative y squared as negative 1 times y squared. Since negative 1 equals I squared, negative 1 times y squared equals I squared times y squared equals yi squared. So x squared plus y squared equals x squared minus yi squared equals x plus yi times x minus yi, which is the factor as a difference of two squares. The factors of x squared plus y squared are x plus yi and x minus yi. How can you use complex numbers to factor the sum of two squares? How can you factor the expression 12x squared plus 3? I can notice that I can actually take out a 3. I can factor out a 3, which would give me 3 times 4x squared plus 1. Well, I can, again, rewrite this as negative I squared. It's the same thing as positive 1. So I have 3 times 4x squared minus I squared, which is the difference of squares. So I can rewrite this as 3 times 2x plus I times 2x minus I. So my factors are 3, 2x plus I, and 2x minus I. All right, so let's go ahead and try it out. Factor each expression, 4x squared plus 25. So 4x squared would really be saying 2x times 2x, and then 25 is 5 times 5. So when I rewrite this, I get 2x plus 5i times 2x minus 5i. 8y squared plus 18, I can factor out a 2, which gives me 4y squared plus 9. 4y squared and 9 are both perfect squares, so 4y squared equals 2y times 2y, and 9 equals 3 times 3. So when I factor this out, I get 2y plus 3i times 2y minus 3i. So I get 2 times 2y minus 3i, because I factored out a 2 in the beginning, times 2y minus 3i. All right, example 6, solve a quadratic equation with complex solutions. How can you solve x squared plus 4 equals 0 using factoring? So x squared plus 4, they're both perfect squares, so I get x squared minus 2i squared equals 0. So x plus 2i, x minus 2i, and then I just solve for x. All right, so let's try it out. X squared plus 49, so x squared equals x times x. 49 equals 7 times 7. So when I do this, I have x plus 7i, x minus 7i, so that's my factors. Oops, it'd be helpful if I actually type in 7 and not y. Okay. So I can take each of these and set them equal to 0. So when I solve, x equals negative 7i, and then x minus 7i equals 0. I add 7i to both sides. So x equals negative 7i and 7i. Do the same thing with 9x squared plus 25. So 9x squared, again, it's perfect square. 3x times 3x, 25 is also perfect square, 5 times 5. So I get 3x plus 5i, 3x minus 5i. So when I solve this, 3x plus 5i equals 0. 3x equals negative 5i, and then x equals negative 5/3 I. I do the same thing with the other one. So I get x equals negative 5/3 I and 5/3 I. You can also write it with the I in the bottom. All right, so concept summary, complex numbers and operations. The imaginary unit I is the number whose square is equal to -1. So the square root of -1 equals I. So I squared equals -1. Big thing that you need to come away with. I squared equals -1. Okay. Complex numbers are written in the form A plus BI. A and B are real numbers and I is the imaginary unit. Treat it like a variable. The 4 basic operations can be applied to complex numbers such as 2 plus 3i and 5 minus I. You can add them, subtract them. When you do this, add or subtract the real numbers first, then add or subtract the imaginary component numbers from each other. Just like variables, you cannot add real and imaginary units together, other than showing that 7 is real and then 2i is your imaginary unit. I can't say that that's 9i though. That's not true. So then I have multiplication. Multiply just like you normally would. Remember, anytime you get an I squared, it's going to be equal to -1. So you need to go back through and solve for those. And then division, multiply both the numerator and denominator by the complex conjugate. So you need to multiply the number and denominator by the conjugate of the denominator. So in this case, 5 minus I is 5 plus I. The only thing that changes is the sign in between.